So my third presentation will deal with ceramics for medical applications, and that's quite an ambitious title to say that we will give a picture of the next 20 years, but as you see, there is an integration point. So my talk will be devoted mainly to orthopedic domain. So first I will give briefly the clinical use, the standard use of ceramics in orthopedics, what are the current solutions and what are the main limitations, and then I will go towards the need for tough, strong and stable bionert ceramics. We have talked about toughness and strength before. We have to talk also about the stability of ceramics. So we foreseen for the next 5 years the use of alumina zirconia-based ceramics and composites, and maybe in the future clinical use of their nanostructured versions, so nanostructured ceramics and composites. And then I will go towards the need for tunable bioactive ceramics with the use of porous bioactive glasses bone substitutes, the use of organic, inorganic scaffolds, and new materials and concepts through biomimetic approaches. And then I would like to conclude my talk with what could be the future position of ceramics in a gradual surgical approach. So we have already talked about ceramics for hip joint application, but just let me summarize what are the specifications for this use. So as you know, ceramics have been used in the form of alumina, mainly alumina, and also, let's say in the 90s, with YTZP. So bioinert ceramics are used for hip and foreseen for knee joint applications, and today we used alumina and still some companies sell some zirconia. So the specifications are quite demanding, so because we used ceramics for generation of the femoral head for the cup, and so we have to resist wear, so that's the first issue and the main issue in orthopedics. So these are two bearing surfaces. As we said before, ceramics are well suited since they have low roughness, also low wetting angles, high hardness, so low wear rate. We have also to resist significant mechanical loading, especially when you are walking or running. You have several times the body load which is applied to the hip joint. For example, for the hip joint, only by walking, this is 4 times the body load. For the knee joint, it can be 6 to 8 times the body load. So that's quite significant mechanical and demanding loading. So as we said before, alumina has a modest crack resistance, and that's why YTZP was used in the 90s because of phase transformation toughening. And of course, the material have to stay in the body for more. We expect more than 15 years. So it should be stable all along this life. So there should be no aging, no change in the material within 15 years or maybe more for the next generation of prosthesis. So ceramics are inert, we know that, but we have to talk about low temperature degradation of zirconia also. So we have seen this before in my first presentation. We can have some failures. The failure rate is very low, less than 0.1%. We said for Biolox alumina, for example, 0.02%, so that's quite low. But we are limited in terms of designs with alumina. So we have designs which are limited in the case of alumina. We have also talked about slow crack growth. That's another important issue. I won't go again into details in the process, but we know that ceramics are sensitive to slow crack growth, so we need ceramics with a higher resistance to slow crack growth. If we take biomedical ceramics, unfortunately, they are all oxide ceramics. Alumina, zirconia, hydroxyapatite, tricalcium phosphate, all calcium phosphate-based ceramics are also oxide ceramics. So we expect that so far, all bioceramics are intrinsically sensitive to slow crack growth, especially stress corrosion by water molecules. We also investigate that aspect, and we said that it was important to investigate threshold below which no crack growth should occur, and of course the toughness. But for delayed failure, what is more important is the threshold. And we can say that there will be no fracture at all, no risk of fracture if the applied stress at the implant is everywhere lower than a limit, which is quite simple to calculate. This limit is given by the ratio of the threshold, K10, upon the square root of the crack size. So we can play a role on the process, because the crack size is here, and we can play a role, and we have shown that before, on the threshold below which no crack growth occurs. So we know that larger threshold will mean larger range of designs without any risk of delayed failure. And so the current solution have now low failure rates, but on a limited range of designs. We are not able to make Alumina 22mm heads. There is a risk of failure. We are afraid to use Alumina alone to make knee joints. Sorry. Another important issue in orthopedics this past, let's say, 10 years is aging of zirconia. This is more a reliability issue. And aging is a slow surface degradation with time. So let's take the surface of a zirconia femoral head. So this is before any aging. And let's put this zirconia inside steam sterilization autoclave. And after 3 hours in autoclave, so at 134 degrees C in 2 bars, there is still no measurable monoclinic content at the surface, but you can see with optical microscopy images, these are Normaski contrast images, so you can see the relief. You can see some white spots, meaning that you have some surface uplift at the surface, after only steam sterilization for 3 hours in autoclave. And then, step by step or with time, there is an increase of the size of these spots with time, and the number of sites increases also with time. So this is a kind of nucleation and growth mechanism in which the monoclinic phase is progressively invading all the surface of the zirconia. So this is after 3, 5, 7 hours in autoclave. So we have done this on zirconia femoral heads in '99, so that's quite a long time. And people said, it should be no problem in vivo because you are working at 144 degrees C, so much higher than the in vivo situation. But what we expected at that time is that due to water, there is a transformation of the grains at the surface. So imagine there is one grain at the surface in contact with water. This grain is transforming. Due to the transformation, you have microcracks and tensile stresses on the neighbors. So the neighbors are transforming. And neighbor by neighbor, the transformation occurs. So what is happening now in vivo? That's most important. Here is the monoclinic surface fraction, so the amount of aging of zirconia. Tetragonal to monoclinic transformation means aging, means degradation of the surface, versus time in vivo. What we expected in some batches from this accelerated test was here. And here you have a plot of different retrieval analysis from us and from other colleagues. So what we see first is that there is a large scatter in the data. But anyway, for most of the prostheses, after some months or some years in vivo, there is a significant amount of degradation. So we have to say that these 3 experimental data are consistent with our simulation because it was the same batch of material. We are lucky to find retrieval analysis, to make a retrieval analysis on the same batch. So our simulations are quite okay and in agreement with experimental data, but what is important that there is a large scatter. And for example, for this prosthesis, after only 2 years in vivo, almost all the surface is degraded. So that's not acceptable, of course. What are the consequences of aging of zirconia? First, as we have surface uplift, because remind that phase transformation occurs by an increase of the cell or of the zirconia, so an increase of the volume of the grain, there will be some surface uplift with time. We see it clearly here. This blank white zone is related to surface uplift at the surface. So if you're wearing against polyethylene, for example, you have wear rate increase of the polyethylene due to this surface roughening of zirconia. That's the first point. Also, this is a micro-cracked zone because we said that the grain, while transforming, leads to micro cracks all around the area. So grain pull-out is quite easy. So roughening and grain pull-out. Here is the surface of zirconia thermal heads after some years in vivo. Not many years. I don't remember exactly, but 3 to 4 years. What you see is that you have some craters at the surface of the zirconia implant. This is due to the fact that this transform zone has been pulled out, and you have a lot of pull-out, and this crater means transformation, and so this grain pull-out. So the consequences of aging are clearly roughening and grain pull-out. This means wear debris, and remember what we said in the first presentation. Wear debris means tissue inflammation, bone resorption, and then aseptic loosening, and the need to change the hip component. Another important and maybe catastrophic issue is that you create defect. A crater like that is a big defect, 10 microns or more in size. You have to remind that it's a large flow, much larger than the grain size, for example. So this large flow can propagate due to slow crack growth, and then you mean delayed failure. And that's what's the case, for example, of Saint-Gobain-Desmarquet prosthesis in 91 and 92. So defect creation means slow crack growth and risk of delayed failure. So we want tough and strong ceramics, but we want also stable ceramics. So that's why we said maybe we can use zirconia toughened alumina. So that's the first strategy, and it's already under clinical use from Ceramtech in the form of Biolox Delta ceramics. So this is a Biolox Delta ceramics mounted on a hip simulator. So the pink color is due to an addition of chromium, but it's quite a standard classical alumina zirconia composite. And we said we should have a higher crack resistance of these composites. But what about stability? We have to know about stability. So when you had alumina, or when you have an alumina matrix and isolated zirconia grains, you have almost no problem with aging. So this is, for example, the amount of monoclinic content we measured after a certain time of aging versus the volume fraction of free white ZP in one composite. So it ranges from 5% zirconia in an alumina matrix towards more than 50% of zirconia in the alumina matrix. And this is zirconia alone. What you find is that the lower the zirconia content, the larger the stability of the material. That's quite obvious. But what is important is that below the percolation threshold, in terms of volume fraction of zirconia, so below, let's say, 16% of zirconia, there is almost no aging at all. So you can process a tough and strong ceramic based on the tetragonal to monoclinic transformation of zirconia during crack propagation, but which is quite highly aging resistance. I just want to emphasize these two graphs in which I have an alumina zirconia composite in which we have quite large zirconia aggregates. Unfortunately, with this composite, you will have aging of these aggregates. So if you process an alumina zirconia composite, you will need to have a perfectly homogeneous dispersion of these zirconia particles inside the composites. If not, you will have aging of the zirconia aggregates. So it is before aging, not the same aggregate, but before aging, and after aging, this zone has been degraded by aging. So alumina zirconia composites can be a first answer to toughness, strength, and good stability. So we said in the previous presentation that we are able now to process micro, nano, and nano composites. So this is the schematic examples of a micro nano composite in which we have zirconia particles inside an alumina matrix. So this is a nice photo I showed you before. And also we are able to make nano composites in which both zirconia and alumina are in the nano size. So this is a composite which I call micro nano. The alumina is on the micron size, the particles are nanometric, and the nano in which all the phases, both phases are on the nanometric scale, few hundreds of nanometers at least. So this is alumina with pure zirconia. That's important to say. This is alumina with pure zirconia. Important to say also this is alumina plus ceria stabilized zirconia ceramic. We said, or I think someone said before, that we are able to, within the NanoCare project especially, we try to do so, we are able to make nanopowders, composite nanopowders, without using, we are able to process nanostructured composites without handling real nanopowders. So the ideas of partners in the NanoCare project is to post-dop a powder, let's say an alumina powder, with a precursor of zirconia. It can be an alkoxide, or it can be also inorganic salts. Then you post-dop submicron alumina, make thermal treatments, and by these thermal treatments, the precursor forms first a vitreous phase, an amorphous phase, and then increasing the thermal treatment, you have particles, zirconia particles, strongly attached to the alumina, which are formed with temperature. And playing with the temperature of the thermal treatment, you can play with the zirconia grain size. So changing the thermal treatment, you can change the amount and especially the size of the zirconia particles. So you can tailor really your micro nano powder with the thermal treatments quite easily. And you do not handle any nano powder, since this is a micro powder and a precursor. And then you obtain something like that, in which you have an alumina grain, in which you have zirconia grains which are strongly attached, really nano zirconia grains which are strongly attached to the alumina powder. So with this kind of strategies, you obtain real materials like that. Here is V versus K1 curves. I've bored you with this V versus K1 curve today, but that's important for implants especially. This is alumina, YTZP, so current solution in orthopedics, I think also in dental field. This is conventional ZTA, and this is the nanomicro and the nanocomposites. So with both, we have a strong increase of the threshold. So we have now clearly new options for future ceramic implants. This means if we have larger threshold, this means that we have wider range of designs. We will be able to process hip and knee resurfacing implants, which are minimally invasive. Again, I can see this poster. This is a minimally invasive implant, resurfacing implant, much less invasive than current implants. And we foresee the first clinical use of ceramic knee prosthesis based on that composites. So what about the resistance of real parts? Because I said before, okay, you can show nice strength, nice toughness on small samples. What about components? So we have made some crack resistance or failure, load to failure of these nanostructured versions of ceramic composites. And the FDA standard approach to make so is this way. So it's quite a simple compressive test, burst test, in which the femoral head is here, and so you push towards the metallic taper until the ceramic break. So what about this new alumina zirconia nanocomposites prototypes versus current alumina and current TZP ceramics? So here is the load to failure of commercial alumina. So 7 tests were done for each material. So this is the standard deviation. Zirconia, 3YTZP. So reminder, modest crack resistance, stable. Here, high crack resistance but not stable. And here, what you find is highly resistance and highly stable. In terms of numbers, the FDA specification limit is 46 kilonewtons, so that's quite a lot. You have to resist 46 kilonewtons for this type of femoral heads, and we resist clearly much more than that, 67 kilonewton, compared to less for the TZP for this kind of design, and much less for alumina. So we have now a new generation of ceramics meeting the demand for high toughness and stability. And I would say that for these two composites, no decrease of strength was shown even after 50 hours in autoclave. Believe me, it's about 150 years in vivo, so there's much more than reasonable. So we can go now to new device concepts. The idea is that current solutions are this. The real current solution clinical use is metallic femoral stem, generally metallic, sometimes a ceramic femoral head, and a polyethylene cup. Don't you think it's quite invasive for the bone stock? When the clinician has to place this, he has to cut the natural femoral heads, to drill a hole here and to place these large pieces. So the idea today is to make minimally invasive implants. And that's the way we are thinking today, is to use these nanocomposites to make minimally invasive ceramic implant for the first time. So this kind of hip joints, much less invasive than current solution, and also knee joints. Sometimes you have only one condyle that is degraded due to a problem with cartilage. So just change what you have to change and not a lot of bone stock. So this is the first part of this talk about the future of ceramics. Now we are going to the, yes, I have 22 minutes left. So we are turning towards the bioactive ceramics, especially for bone substitute applications and tissue engineering. So the idea of this bioactive ceramics is to put a ceramic, or material in general, as a bone substitute which should induce or could induce a positive bone response and favor bone ingrowth. So let's talk about first bone. What is the bone structure? What is the bone composition? Here is a bone, not a human bone, but a rabbit bone. You can see some a structure like that. So it's open pores like that, a structure like that at low magnification. And higher magnification, you can see that there is a specific roughness at the surface, and still higher magnification, what you can see that there is a micro roughness at the surface of the struts, of the pores. So this means that, and we know that, there are some hydroxyapatite grains, but they are very, very, very small. So the bone is consisting, for the mineral part, of hydroxyapatite grains, but at the nano level. So the hydroxyapatite grains in bone are really nano. And concerning the composition, of course, we have an inorganic phase, 60 to 70 weight %, which is calcium phosphate, a kind of hydroxyapatite, to be simple. And also there is an organic phase, which is collagen. And organic phase plays a great role on the toughness and the energy to failure of the bone. And of course, we have the cells. So if we make bone substitutes, we have to clearly think about the bone cells and the bone cells which are responsible for bone remodeling. Each year, you remodel about 10%, even the adults, 10% of your bone is remodeled each year. So in 10 years, all the bone is remodeled completely. So we have bone cells that are responsible for bone remodeling. If not, bone is too brittle, is too fragile. So we have here in this picture, given by a biologist, the green part is the bone, which is already formed. What we can see here is that a part of this bone has been damaged, has been resorbed by some cells. So there are some cells responsible for bone resorption. And these cells responsible for bone resorption are called osteoclasts. Clasts for hold. So this means that these cells are responsible for bone resorption. So in your bone, you have cells that are responsible for active for bone resorption. And after this bone resorption, you have other cells that are responsible for bone reconstruction. So after resorption by some cells, there is a reconstruction with other cells, which are called osteoblasts. So here is a new bone, which is highly rich in collagen, in organic phase, which have been reconstructed by these cells. So of course, you have to take into account what is the activity of these cells versus your new material for bone substitution. And especially for bone remodeling, we need ionic exchanges with body fluid, and especially calcium and phosphate. So that's why we use calcium phosphate ceramics and glasses. So what is the current clinical use? We already use calcium phosphate ceramics, So here is a natural bone, especially the mineral part of this natural bone, and here is a synthetic calcium phosphate bone substitute we have made, for example, in the lab. So the idea is to mimic the structure of the bone at the micro level. This is 1 millimeter in size, 500 microns in size, so about the same type of structure. So the first idea is to mimic the structure. And especially what we want is to have a large porosity. That's completely the inverse than that for the femoral heads, where we need the lowest defect as possible. Here we need large amount of porosities, especially for cell proliferation inside the bone substitute. So in this picture, it is a cross-section of bone substitutes, and we have put some osteoblast cells, because these are the osteoblasts that we want to study. And these cells are in this cross-section in blue. So we have put some cells at the surface of such kind of substitutes, and after 21 days, what we observe is that all the surface is covered with these blue points, dots. These are cells which have been colored. So all the surface has been covered by these cells, and more important, the cells now have proliferated inside the bone substitute. What you see here in blue, this is the path followed by the cells among the interconnection between pores. So of course, interconnection between pores is really important for this kind of material. So what you see is that the cells are able to pass through the interconnection, and then they adhere to the surface of the pores. So what might be important also is the microporosity you have at the surface, or micro-roughness you have at the surface of the pores. So an important factor is the interconnection between pores, so the macro interconnection between large pores, but maybe also important, clearly also important, is to play with the microporosity. What is the roughness at this surface? And what we have seen is that osteoblast cells really like very much micro-rough surfaces. So here is osteoblasts, which was observed under environmental scanning electron microscopy images. And you can see this osteoblast hanging onto the microporosity. I'm not a biologist at all, but when I see that, so this is the extension, cytoplasmic extension. It's like the arm of a climber that tries to attach to the surface. So they need surface micro-roughness. So interconnection with pores and microporosity is really a key factor for using bone substitutes. So what about, let's say, future? So it's quite near future, since we already have developed this and it's already sold by a company. We can incorporate drugs. So you can play with these calcium phosphate ceramics by making drug release. And especially what we have made, simple strategy to release antibiotics. And it's important to release antibiotic at the site where you implant the bone substitute. And you play with the microporosity again. We have a microporous body. So the idea is to impregnate with antibiotic. So here is a large pore, and between the large pores we said that we have a lot of microporosity. So we can fill the microporosity with antibiotic, impregnate it. So we can see that here is antibiotic filling all the microporosities. And after 48 hours, not less, not more. So not less, why? Because if not, you have too much antibiotic at the same time. Not more, if not, you have some resistance of the bacteria to the antibiotic. So with 48 hours, there is no more antibiotic in the bone substitutes. And we have tested that also on animals, and now it's on the market. So how to play with that? You have to play with the porosity features, pore content, pore size, for the speed of diffusion. So one important problem, or one problem with calcium phosphate today is their mechanical strength. Again, mechanical strength. I am a monomaniac. What you see is the toughness. Hydroxyapatite, tricalcium phosphate have a toughness of only 1. This is about the same as the glass. So these are really brittle material. So one way of improving their properties and their application is to improve their crack resistance. Another important factor is, are we able to make nanostructuration? Because if you look at these pictures, the grain size, okay, so this is some microns in size. The grain size is about 1 micron or something like that. So can we decrease the size and go towards nanostructuration? So we can make nanostructured bone substitutes by using bioglasses. What we have shown is that using bioglass powders, you have the opportunity to profit some transition and some crystallization process. When you take a bioglass, at 550 degrees C, you have a first glass transition, then the glass-in-glass separation, and then the rapid crystallization of this crystalline phase. And then at this temperature, you have a crystallization of a second phase, and then if you go towards larger temperature, you have a second glass transition. So you can play with this crystallization process to sinter nanostructured glass ceramic porous bodies. And we have shown that the crystallinity changes the, let's say, changes the bioactivity of the bioglasses. So here is here are the image of bioglass derived porous scaffolds. We think, because this is the idea of what could be the next option, this can be really an interesting alternative to calcium phosphate. So we have worked on that, especially also with a group in Imperial College, Aldo Boccaccini and co-workers. We have shown that with bioglasses, it's possible to control crystallization process. We have really nanocrystals, and it's possible to control the porosity by sintering bioglass powders. So here are some images of a porous bioglass scaffold. Here is the image at higher magnification of this scaffold, the strut, after a given amount of time in the simulated body fluid. After a certain amount of time under body fluid, we can see some carbonated hydroxyapatite at the surface. The same type of hydroxyapatite than that we have in the body reading. So these are these really nice, very small nanocrystal of carbonated apatite. And what is important is that we need to show and to check that the osteoblasts, the real cells, adhere and proliferate on the surface and through the porous blocks. And that was really the case. These are images taken by confocal microscopy, so you can see in depth inside the porous substitutes by optical microscopy. And these are confocal micrographs of cell proliferation and also metabolism kinetics on bioactive glass porous blocks. So here is, let's say, here is the surface of a pore. After 9 days in simulated body fluid or cell cultures, the cells are proliferating inside the bone substitutes. So the cells are in red, and with time you have an increase of the proliferation of the cells inside the bone substitutes. And what is maybe more important is that the cells are able to produce type 1 collagen. So this means that they are forming new bone inside the substitutes in vitro. So now you can talk about tissue engineering, acting with these bioglass scaffolds to favor osteoblast proliferation and formation of new type of bone. So concerning the mechanical properties, how can we improve the mechanical properties of these calcium phosphate or even bioglass scaffolds? Playing with organic matter. So this is an example of a sintered microporous ceramic scaffold which is impregnated with a biopolymer. So the method is quite simple. You have a porous scaffold and you impregnate the microporosity with a polymer, especially biopolymer. And then you make strength measurements. You make some mechanical tests. What we obtain is that here is the ceramic, here is the crack, and you can see some bridges. What are these bridges? This is the organic matter. So we have some organic fibrils that act to resist crack propagation. So we have an inorganic, organic composite, and when a crack or microcrack propagates, you have bridging by these fibrils. like in bone. In bone, you have collagen that is able to bridge microcracks in the mineral phase. And what are the results in terms of really of the energy to failure? What is the quantification of that? Here is the apparent fracture energy for different materials. So this is pure alumina. This is alumina impregnated with polymer with nanoparticles, impregnated one with a solution, and impregnated twice with an organic solution. So this is here pure ceramic, so very low apparent fracture energy. And here is the composite in which we have impregnated twice the ceramic with a polymer. Let's have a look at the results. It's more than one order, almost two orders of magnitudes in terms of apparent fracture energy. So we cannot increase the strength. The strength is the same, but what is important is that the energy to failure is much more important in this type of inorganic compounds. So Tony Tomsia, I think, talked about this biomimetic approach. So just 1 minute to confirm that also this is really an interesting way for the future. So you can make biomimetism in the terms of using nacre as a biomaterial. This is the approach of some French teams, especially Lopez and collaborators. But maybe more interesting is to use nacre as a source for materials engineering. So try to mimic the structure of nacre in real synthetic material. So the structure of nacre is structured at different levels, and especially we have platelets like that. And Tomsia and co-workers were able to process something which is really near the structure of nacre. You have here real natural nacre, and there is a material in which you have platelets like that. And they found really impressive toughness values and toughness measurements. So this is my concluding remark concerning this talk. What can be the future position of ceramics in a gradual surgical approach? So let's take a surgeon. What can be the first answer? The first answer will be, or should be, tissue regeneration without any biomaterial. So just say just with drugs or something like that. So that can be the first answer to trauma or disease. If the disease is not so big that you can try to make tissue regeneration without any biomaterial. So there are large progress in this field, and we believe that it should work in the future. The second answer will appear, tissue engineering assisted by bioactive scaffolds. So this is the second answer. If the disease or the trauma is too important, you will need a scaffold, a material to induce bone ingrowth. And after this inducing of bone ingrowth, then the material has to disappear. So if it's possible, we should have bioactive osteoinductive material which are resorbable. And that's possible thanks to some osteoinductive scaffolds that I've shown before. The third answer will be surgery. Anyway, for some patients, we will need, even in 20 years, surgery. So what about this answer to this kind of surgery? We should use minimally invasive implant as the first answer. So we should use an implant that preserves the bone stock. And that's the case of hip resurfacing implant and uni-knee, as we discussed before. And then at last, and for sure, I'm almost completely sure, the last answer will still be conventional implant. But that will be the last answer to this kind of problem with bone and cartilage. So we will use conventional implant, but use conventional implant able to maintain the highest level of bone stock, and of course, as we said, tough and stable. So I finished. Thank you for your attention.